Hey everybody! Today I want to talk to you about programming your microprocessor. Back in CAD 1133, we designed a circuit board and we talked a little bit about programming it. And it wasn't until you started to get into your MPRO that you really, in earnest, started doing programming of microprocessors. Today, I want to talk to you a little bit more about microprocessors and particularly about using a tool called MPLAB. One of the great things about MPLAB is it's actually written and created by Microchip, so it's designed for their chips. One thing that is not common knowledge is that there is a plugin that we can actually write a program and simulate in Proteus. And so I want to today I'm gonna break this down into two parts. We're going to create a program, just a simple blinking light, and we're going to simulate it in Proteus, and then I'll actually burn it to the development board that we worked on in the winter. And anybody who hasn't been in my class, if you're interested and you have access to Proteus, that's fantastic. If not, we're going to talk about some straight up programming and how to use MPLAB using XC-8 as our compiler to create and write a very simple program. We're going to talk a little bit about registers. Okay, so let's dig in. Okay, so let's start with our Proteus file. Here we are. Now I've taken our Proteus file from CAD 1133, which for anybody who hasn't taken my class, this is simply a PIC 18F26K22 microprocessor. And the pins that we're going to deal with today are register RA5, which is pin 7, and the RC1, which is pin 12. Okay. And other things that we need to make sure that we do. One of them is I have a simple transistor set up to be syncing to ground. And the idea is what we're going to make our program do is turn on RA5, so it's sourcing, and we're going to pulse pin register C1, this pin CCP. We're going to pulse it to make the light flash. Other things that you're going to want to make sure you do when you're setting up your microprocessor is to make sure that the memory clear is pulled high, and that should be all you need for the pin connections. Now we want to make sure that two things. If you are using your file from CAD class, make sure there is no program file associated with it, and that it's set to 8 megahertz. You may be best to put a new file together, because if there is anything associated here, it will interfere with what we're going to do today. And I've created just a desktop folder to put this in so that all of my files end up in the same place. Okay. Now, the next thing that we want to do is we want to download and install MPLAB X, and I've been having some trouble with the latest revision, so I've gone back to using version 5.30. It seems to work stably for the plugin. 5.35 works fantastic for everything else, but yeah, I couldn't get it to work, and it's caused me days of frustration. So I've reverted back, and we'll use this to get started. And so let's start by looking at what you need to download. So definitely you're going to want to have XC-8 downloaded. If you need help on that, we can maybe take a look at that. But one thing that you will definitely need is under Tools, plugins, and I'm going to have to go to installed. You'll find yours under available, but the one that you want is the Proteus VSM viewer. So go ahead and install that. Okay, so we're going to go ahead and create our main file. Now, in order to do this, we're going to need to go in and say that we want to create a new Microchip embedded standalone. Next. The processor that we're using is an 18F26K22, and so we'll choose that. And instead of picking one of our programmers, we're going to go down to the Proteus VSM viewer, say next, pick our XC-8 version 2.10, and we will browse to the folder where you want it. Okay, I'll say open that folder, and we will give it a name. For example, Blinky_1, and I'll say finished. And here we go. There's Blinky1 made, and you'll notice that the folders that it creates, it's nice that it creates the folders, but they are for the most part empty. And so what we want to do is we want to go in under our source files, and we want to create a new main file. And the way to do that is not by right-clicking and saying new main file, but rather saying file, new file, and then we will choose a C file and C main file. Okay, and you'll see that what it does is it creates a main loop as well as or function, as well as stdio and the standard lib files. Okay, so I'll say next. We'll call it new main. That's fine, and we'll finish up. And there we go. So it has the two files that we need, and we'll call that good so far. So one of the first things that you'll find when dealing with microprocessors is that you need to set a lot of registers, and there is no real shortcut for this. In reality, the only way to learn about microprocessors is to sit down with the data sheet and look at each of the registers and set them properly. MPLAB is your first shortcut. It allows you to set up the microprocessor very quickly and easily, but you do need to know what these registers do. But we're kind of going to glaze over that a little bit today, and we're going to use a tool here. And so under the window menu, I want you to go down and you'll find something called target memory views. And you want to go under configuration bits, and it will open up this menu here. Now there's a fair bit in here, and the advantage that I have is that I know what I'm looking for, and I've done this a few times. So play along, but you can set each of these registers here under the options, and it does have a description of what it's doing. And so, for example, this FOSC sets the oscillator, and what we want is the internal oscillator, so int, and we want an IO on pins 6 and 7, and so that's what that happens to stand for, and so we're good on that. And the other one that we can do is the watchdog timer. We want to turn that off for now, because. And MCLR is already set properly, and everything else there is a-okay. So when we're finished, we're going to go ahead and we're going to say generate the code output, and you'll notice it creates this giant file. And all I'm going to do is I'm going to copy it, go back to my main program, and I'm going to paste it in. And look at that, it includes the next thing that we would need, which is XC.H. Now, one neat thing on this is as you're going through and you're creating these include files and functions, is if you hold down the control button, you'll notice that it actually highlights what's some information about it. And if you left click, it will actually take you to that file, and you can read what it does. And so in this case, it sets your optimization and a few things. But we're going to call that okay for now. Okay. The next thing that we would want to do is we do need to actually include the file for the microprocessor that we have. And so I'm just going to include the processor, which is a PIC 18F26K22, and we want to make sure that we get the header file, not the include file. Okay, and what else do we need to include? That's pretty much it. Okay, good, fantastic. So I'm going to change this out, and I want to create, instead of int main, I'm going to create a void main void as my main loop. And there we go. And so this is where our main program is going to sit. And now we're talking about registers, we're talking about setting things up. There's two main things that we need to set as far as the pins. One of them is called tris, and the other one is ANSEL, ANSEL. So tris is for tri-state, and it determines whether the pin is in input or output, and ANSEL determines whether it's an analog or a digital pin. And we need to determine it for both port A, and we'll also do port C. Okay, and we can set these ports. We can set these ports. Darn it. To a value, and we have a couple ways that we can do it. We can use hexadecimal, so 0x, and in this case they're all going to be outputs. Okay, we could use a binary. Okay, or you could use decimal, and you would be probably the only person in the world to do it, but it does work. Okay, you could also set just a single bit, and we'll hold off on that till this next function that I want to show you. Okay, but I'm sorry, I can't actually do it. It's just such bad form. Okay, but we'll leave the other ones. Let's see. Oh, you're right. So the other thing that we want to do is we want to address the state of the pins when we first turn it on. Now there are two registers that we deal with quite often when it comes to GPIO pins. One is the port, one is the latch. What we do is we set a latch, okay, so it's lat, and we read a port, which is port, okay. And so we want to make sure that we set our latches in a condition on startup so that we know what they are. And so in this case, I'm going to say lat A is also equal to 0x00, and lat C is equal to 0x00. 0, 0. Okay. And that should do us pretty much for getting started. And yeah. And so now we can actually put in our main loop. And so the next thing would be to put in a while 1. And so this is going to be our main loop where we go around and around forever. And so we want to turn on that LED. And so let's back up the bus here and let's make a couple defines. Okay. So I'm going to define, and I'm going to call the first one red, and I'm going to set that as latch A bits, and we want to set lat A5, so LA5 as our red, and I will create a second define, and we'll call it CCP, and we'll set it up as lat C bits, and we're looking for LC1. Okay, and so the lowercase bits dot whatever allows us to actually deal with a single bit. No, we won't do that. A single bit in a register. Okay, and so now in our main loop we can actually type in that we want to set red is on, and that should turn our red LED on, and then we will set our CCP is equal to not CCP, which is a shortcut for creating just a toggle. And we would obviously want to slow it down. We don't want it running at the full 8 megahertz of the processor, and so what we need to do is we'll put in a underscore delay ms, and let's put in 100 milliseconds. Okay, and if I try to compile it, this is going to give me an error. It should give me an error saying that it can't define the time register. Hey, what do you know? And so it tells us that one of the really brilliant things about having a compiler like this is it comes out and tells us, hey, you forgot something. And in this case, we want to include, here we want to also define underscore xtel Freek. Okay, and we want to set it to 8, 1, 2, 3, 1, 2, 3. Okay, so 8 megahertz, and that'll help us to resolve the first issue. And so we'll clean and build here again, and this time it loaded nicely. And so we're going to go ahead and go back here to our project properties and go under our VSM viewer for Proteus, and you'll notice there is no file associated. So we'll click on here and we'll associate it with our test project. And I'll say okay and apply, and finally okay. And now, cross your fingers, we're going to run it in debug. So far so good. Found the ELF file, connecting, starts up Proteus again, and sure enough it's running. By the way, make sure that the LED is actually in analog. The rest of the switches and what have you can be in digital, but that's okay. And we see our next problem. Our next problem is, well, this is supposed to be flashing 10 times a second, and it's absolutely not. So you scratch your head, right? What's going on? And so let's go back here for a second. And now I had mentioned that there's a bunch of registers that we need to set up. And so I'm going to stop my simulation here. And I'll tell you, the one that we're missing is the oscillator control. So OSCON. And we need to set it so that we determine what speed the internal crystal is actually running at. We've told it that we want an internal crystal, and we've told them what crystal Freek should be, but we haven't actually set it. And I encourage you to find the data sheet, take a look at it, but you'll find that the first bit is actually has to do with the sleep mode, and the next 3 bits have to do with the speed. And 110 happens to be for 8 megahertz. The last 4 bits don't really matter, so 1, 2, 3, 4, and we'll call that reasonable. So let's go ahead and run this again. There you go. That looks much better. Flashing on and off rather quickly. And so there we go. That's pretty much all there is to that. Now, what advantage does this have? Well, we can very quickly run through and see what's happening with the program. One thing that we can't really do is to do single stepping. It kind of sort of works, but not really. What we can do is actually set up breakpoints, though. For example, whenever we toggle the switch, we could set up a breakpoint. I need to actually stop it. And we'll set a breakpoint. What a breakpoint does is when the program gets to that particular point in the program, it'll stop it. So here we are. We'll do it this way. And so let's run this again. And here we go. We've stopped it, and the light is off. So we'll run it again. And the light. Oh, it's the wrong one. I apologize profusely. Okay, so light is on. We'll hit play again. Light is on, light is off, light is on, light is off. And so our every time we come to that breakpoint, it stops and we have to hit play again. And so, you know, on a program this simple, it's not really a thing, but you can imagine on a very sophisticated program, when we hit something like an ISR, we may want to stop. Okay, so let's call that good enough for now. We're happy that this is running. It's time to actually send it to our board. All right, and so this is what I have for my circuit board setup. So as you can see, it's our development board. I have a snap programmer plugged in. I've used my analog discovery to show us what's actually happening, and we should be able to create a program right now. We're back, and so what we want to do now is we actually want to send this to our development board. And so what we need to do is go back to our little toolbar here. We're going to select that, and we're going to change to our snap programmer, and I'll say apply, and OK. And if we want to double check, we can hit the little circle guy here, and it should tell us that we are connected, that it's able to find. Sure enough, connecting to Snap, current version. It gives us all our build information. Perfect. It's updating the firmware. Fortunately or unfortunately, it does this every time, which is good, that it makes sure that we have the latest revision. But it slows us down a little bit, especially when you live out in the middle of nowhere like I do. And so sure enough, there's our target device. It sees it, and it even gives us the revision number, which if you're looking at the errata, and you should, you can tell what's going on there. Okay, so in order to send it to the programmer, you'll notice that we now have access to the make and program device, as well as upload, but we don't really care about that. Today we're just going to program it. Okay, and connecting to the programmer. This shouldn't take too awfully long. Erasing, program complete. And if I open up my waveforms here and I say run, here we go. We just need to change a few items, make this work for us. So we definitely want to be in 1. We want to set this to how's that look? A little bit more. And we'll set this to channel 2 triggering. And perfect. So what we're seeing is 100 milliseconds on, 100 milliseconds off, and our volts per division is set to 1. So 1, 2, 3, and a little bit to here. You'll notice that it's a little bit low, and that's due to internal resistance in the microprocessor. There's actually a small voltage drop across the FET, and this way we're looking at just the voltage drop across the transistor, so we won't worry about that too much. So let's go ahead and change what's going on here with our program, just to show you how easy this is. In this case, let's change it to 50 milliseconds. Okay, and so we'll go ahead and reprogram it, and you'll see it's quite quick this time. Yeah, I mean, one of the advantages to writing a stripped down program like this is it really does program super fast. And so now you see 50 milliseconds on, 50 milliseconds off. The LED looks like it's having a little fit over here. It's turning on quite nicely, and that's all there is to it. Okay, so in the next video, I'm going to show you another tool called MCC, and we'll upgrade to revision 3.53 of Proteus, of MPLAB, and I'll show you how we can dig into even more shortcuts, and we'll talk about some of the shortcomings. Okay, thanks, and I hope you come back.